Today we're going to practice writing some electron configuration. And we'll also look at how that relates to orbital energy diagrams. So starting with electron configuration, if you remember from the PowerPoints, electron configuration is using the periodic table to describe where the electrons are in a given atom. So to do this, we split the periodic table up into different groups. So first off, we have these numbers on the far left of the periodic table. So period 1, period 2, all the way down to period 7. So these numbers are our n values. So we're going to be using these numbers to indicate which row or period the element we're talking about is in. Now we further split up the periodic table into an S section, a D section, and a P section. So the S section is outlined in red here, so it consists of the alkali metals and the alkaline earth metals. In the case of this S orbital section, this sublevel, helium belongs next to hydrogen because it is a 1s atom. Now the D, that's in the middle here, so it's the transition metals highlighted in yellow. And whenever we're talking about any of the elements in the D, the period they're in, we represent it, it's always one less than the period it's in. So right here I have n-1 D. What that means is whatever period we're looking in is our n value. So if I'm looking in period 5, once I get to the D's, this is actually period 5, so 5 minus 1. These are the 4 D's. So the D's are always one less than the period they're in when we're talking about the n value. Last but not least, we have the P's. So this section over here are the p orbitals. Now also to mention, you can tell how many electrons can fit in each of these orbitals based off of how many groups we have. So for instance, the S, we have 2 groups, so it can only hold a max of 2 electrons. For the D's, counting across, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so it can hold a max of 10 electrons. P's, 1, 2, 3, 4, 5, 6. So P's can hold a max of 6. So let's use this to describe the electrons in an atom. So I'm going to start by describing nitrogen, represented by the chemical symbol N. So nitrogen is number 7 here on the periodic table. Whenever we're describing the electron configuration of any atom, we always want to start in period 1 in the S. So we're starting from the beginning. We're using this periodic table kind of like a map or a maze. So you only have one place you can start. And that's always at this 1s where hydrogen is. So to describe where nitrogen is, I start in period 1. I hit the S block first in red here. Now, how many electrons did we say can fit in the S? Remember, we're looking at how many groups. So there's 1, 2, so a max of 2 electrons. So when I write 1s2, what I'm saying is look in period 1, look in the S block, and this 2 is the second one in. So what that means is hydrogen would be 1s1, helium is now 1s2. So I'm describing helium if I stop there. But I don't want to stop there. I want to keep going because I'm trying to get to nitrogen. So to do that, I need to go then to period 2. When I reach period 2, I hit the S's first. So I'm going to write 2s to indicate this is where I am. Now, if I write 2s2, that means I'm going all the way through the S block. So if I stopped at 2s2, I'd be at Be, beryllium. But I'm going to keep going because I want to get to nitrogen. So I'm still in the 2s, and then I'll hit the P's next. So I'm going to write 2, now I'm in the P's. Nitrogen is in the 2 P's. Which one? It's 1, 2, 3. It's the third one in. So 2p3 is describing nitrogen. Now these numbers that I have up here, These are representing the electrons in an atom of nitrogen. And since we're talking about neutral nitrogen, if you remember about neutrality, when something's neutral, the protons equal the electrons. And nitrogen, since it's number 7 on the periodic table, that means it has 7 protons. So since the protons equal the electrons, that means it should also have 7 electrons. Why am I bringing this up? Because you'll notice if you count these electrons, it equals 7. So 3, 4, 5, 6, 7. So it's a double check that we are indeed talking about a neutral atom of nitrogen and describing that here. Let's try another one. So next, let's look at sulfur, represented by the letter S. Now sulfur is number 16. So since it's number 16, it means it has 16 protons. We're talking about neutral sulfur, so that means it's also going to have 16 electrons. So once I'm done writing out the electron configuration, if I add all of these numbers together, it should equal 16 if I did it correctly. So I need to describe where sulfur is. I'm going to start in period 1 at the S's, just like I did here. So we have 1s, max of 2 electrons in the S block. So I'm at helium now. Then I hit period 2, because there's nothing else in period 1, it's just that 1s. So in period 2, I hit the S's again. I want to go through them, so 2s2, so I'm at beryllium now. Then I'm going to hit the P's for the first time, so it's 2p. Now this time, sulfur, it's not in the 2p's, it's down here in the 3p's. So I want to go all the way through that P block. So to do that, I have to figure out what's the maximum amount of electrons, what number goes here that I can fit in the P block. And we said it was 1, 2, 3, 4, 5, 6. So 2p6. So when I write 2p6, I'm now describing neon. But I don't want to stop there, I'm going to keep going. So I hit period 3 next. I hit the S block, always hit the S block first. The maximum amount of electrons in the S is 2. So now I'm at magnesium. I'm going to keep going. I'm still in period 3. I hit the P block next. Now this time sulfur's in the P block. Which one in? It's 1, 2, 3, 4. It's the 4th one in, so 3p4 will describe sulfur. Now, to double check, I can always count, and these should equal, in this case, 16, because that is the atomic number of sulfur. Let's do another one. This time let's do one a little further down, see what it looks like when we hit the D's, because we haven't got it into the D's yet. So let's do bromine. So bromine is Br. Now notice the beginning parts of all of these look exactly the same, right? Because it's a map starting at the same spot, so you're going to follow the same trail for part of the way, right? So when I go to describe bromine, I'm going to do the same thing. 1s2 brings me to helium, 2s2 brings me to beryllium, 2p6 brings me to neon. Then I'm in period 3. 3s2 gets me to magnesium. I'm still in period 3, and I hit the P's next. This time I want to go all the way through the 3p's. So it's going to be 3p6. Then I get into the 4s. So 4s is what I hit first. And there's a max of 2 in the S. So 4s2, now I'm at calcium. So if I stopped here, I would be describing calcium. But I want to keep going, and notice I'm hitting the D's for the first time. But it's not 4D. Okay, that's incorrect. Because remember, the D's, for the number that goes in front of the D, it's 1 less than the period it's in. So since I'm in period 4, when I hit the D's, I'm going to write 3D. Now, bromine is not in the D block, so I need to go all the way through it. So I need to get to zinc all the way through it. And remember, for the Ds, there's 10 that you can fit in there. So I'm going to write 3D10 to bring me to zinc. Then notice at zinc, I hit the P's again with gallium. I'm going to go back up to 4, because when we're talking about the P's, we want the number to be the same as the period it's in. So 4P. And bromine is 1, 2, 3, 4, 5. Fifth one in. So now, if I count all of these guys, it should equal 35, which is the atomic number for bromine. Number of protons equals the number of electrons since it's neutral. All right, so as you can see, the further down you go, the much longer these get. So I do want to show you a shorthand notation way. So there's a way to write this shorthand where you don't have to do the entire thing starting at 1s. And the shorthand way is actually called the the noble gas shorthand. So it's called noble gas shorthand because you're using the noble gases to express it. So for noble gas shorthand, the rule is you can start at, instead of starting at 1s, you can start at the noble gas in the row above the element you're trying to describe. Okay, so for instance, let's do all 3 of these so we can see a couple examples. Neon is the first one. So the noble gas shorthand says I can start, instead of starting at 1s, I can start at the noble gas in the row above. So nitrogen is in period 2, so I want to look at the noble gas in period 1. And the noble gas in period 1 is helium. So I can start by writing He, helium, in brackets, and then that takes care of this portion. Because helium is 1s2, so I just described it by writing He, so I don't need to write this part in the shorthand. What I do need to include is everything after helium. So I still need to include the 2s2 and the 2p3. So this would be the shorthand way of nitrogen. Now I know it doesn't seem that shorthand, but nitrogen's a short one to begin with. So let's look at a longer one, and that one being sulfur. So for sulfur, it's in period 3. The noble gas shorthand way, I'm going to do brackets, and I'm going to put the noble gas in the row above sulfur. So the noble gas in the row above sulfur is neon. Remember, the noble gases are this last row here. Okay, group 18. So when I write neon, what I'm describing is this whole section here. Because look, 2p6. Okay, period 2, p block. 1, 2, 3, 4, 5, 6. So that 2p6 describes neon. So I don't need to write any of this because I wrote Ne. So I can take that part out. Now I start after neon, which is period 3. 3s2 brings me to magnesium, and then 3p4 describes sulfur. So this would be the shorthand way to do sulfur, to describe sulfur. Now next, let's look at bromine. So bromine is in period 4. So you want to use a noble gas in the row above, which is argon. So I'm going to put argon in brackets. And that takes care of, so argon is in period 3, and it's 3p6 to be exact. So I can cut out this entire section up to 3p6. But I do need to include this part. So I can start at 4s2, 3d10, 4p5. So this would be the noble gas shorthand describing bromine. Now let's try, given an electron configuration, to figure out which atom is being described. So in this first one, the key piece of information to figuring out what atom is being described is just this last piece here. Because the 3 tells you which period to look in, The S tells you which block, and then this superscript number tells us which one in that block. So it's saying look in period 3. So I'm in period 3. They're saying look in the S block. So it's going to be one of these two. It's either sodium or magnesium. How do I know which one? The superscript here. S1, it's saying the first one in the 3S. And the first one in the 3S is Na, sodium. The other way you can figure this out is, remember we said that these superscripts, numbers, represent the number of electrons. And we're talking about all neutral compounds here, so electrons will equal the protons. So if I add these numbers up, I get 6, 7, 8, 9, 10, 11. So it's telling me, find number 11 on your periodic table. Number 11 is sodium, the atomic number 11. Okay, so there's two ways you can do that. Now the next one, notice noble gas shorthand. I got brackets and a noble gas inside of the brackets. So this is telling me, okay, start at krypton. So I can start at Kr in period 4. Then I have 5s2, brings me to strontium. I hit the Ds, so that's why it's 4D. Ds are always one less than the period they're in. So 4D10 brings me all the way to cadmium. And then I hit the Ps, so 5P, and it's the fourth one in. So remember, this is the only piece of information you really need is this last piece here. Oops, excuse me, 5P4. So period 5, P block, and the fourth one in. 1, 2, 3, 4. Te. Trillium is the answer for that one. Let's try one more. So looking at this next one, remember it's just the last piece of information. It's going to help us find the atom. It's saying go to period 3, go to the P block in orange here, and it's the second one in. So period 3, I hit the P block, 1, 2. Second one in is silicon. And since this is written the long way, the longhand way, you can take these numbers and add them together, and they should equal the atomic number of silicon, which is 14. Okay, now, last but not least, we're going to take this, and I'm just going to do the last one here of silicon, and we're going to draw the orbital energy diagram of it. So what an orbital energy diagram is, if you remember from the PowerPoints, it's a representation, a way of writing the electron configuration in a pictorial diagram. So an orbital energy diagram, so let me not write that. Here's the nucleus. And then the energy is increasing as we go up. So we have 1s, 2s, 2p, 3s, 3p, 4s, 4p, so on and so forth. So you can keep writing it up. So you'll notice these are following the same order as the electron configuration. You start at the 1s, lowest energy, you move up to the 2s, then the 2p, then the 3s, then the 3p, so on and so forth. You'll also notice the s's, they only have one blank space. So the reason the s's have one blank space is because they can only hold 2 electrons. So one of the rules when filling these up is that each orbital, which that's what these little spaces represent, can hold a max of 2 electrons. And not only can they hold a max of 2 electrons, but the 2 electrons that we put in there must have opposite spins. Meaning, when we draw it, we're going to represent the electrons with arrows, and we're going to make sure the arrows are going opposite directions when we pair them up. So if I were to fill in this energy orbital diagram for silicon, what I would do is I see that I have 14 electrons that I need to use. So that's how many electrons are in a neutral atom of silicon. And I would start by putting 2 electrons in each empty space. And you always start at the lowest energy level first. So that's another rule for filling these out. So start at the lowest. And work your way up. So I've used 2 electrons, 1s, 2. Those are my 2 electrons in the 1s orbital. Then I hit the 2s. 2 electrons there as well, opposite spins, opposite directions. Then I hit the 2p, and there's going to fit 6 in there. That's why there's 3 spaces, 2 electrons in each. 2, 4, 6. So that's my 2p6. I'm going to keep going. I get to the 3s, 2 electrons in there. And then the 3p, there's only 2 electrons. Now here's something, another rule that you need to apply when filling these out. And this rule applies to p and d orbitals only. And that is, apples, applies, there we go. That is that when you are filling a p or a d, you always want to spread apart the electrons as far as possible before pairing them up. So what I mean is, I have these 2 electrons. What I don't want to do is put both of them together in one empty space. Why? Well, these are electrons. Electrons are negatively charged. Like repel, they don't want to be close to each other if they don't have to be. So you don't want to pair up the electrons unless you have to. We had to pair them up here because there was 6. And in order to fit all 6, I had to put 2 in each. But for the 3p, there's only 2 electrons in the 3p for silicon. So I don't have to pair them up if I don't want to. And they don't want to be paired up. So what I'm going to do is I'm going to put 1 electron in this space and 1 here. So that's the correct orbital energy diagram of silicon. So know those 3 rules when filling an orbital energy diagram, and then also be able to pair one up in a multiple choice question. So I want to kind of, last thing here, configure this into what we know about an atom, because this is really just a picture of an atom. Remember, these are representing the electrons. So these are actually the rings, if you will, that the electrons sit on that we talked about when we talked about the structure of an atom. Okay, so we have ring, ring, ring. So we have 3 rings. The first ring is the 1s orbital, and it has 2 electrons. The second ring, 2, 2, so all of these electrons in 2 are on the second ring. So we have 2 from the s and 6 from the p. So that's a total of 8 on the second ring. And then last but not least, on the third ring, we have 1, 2, 3, 4. 2 from the 3s and 2 from the 3p. Now, these electrons on the outer ring, these 4, are the valence electrons. These are the ones that are involved in bonding when we talked about covalent bonds, where they're sharing electrons, ionic bonds, when electrons are transferred. That's only the valence electrons that are being used to make those bonds. So in the case of silicon, it is just these 4. And we also talked about silicon in group 14. Everybody in group 14 has 4 valence electrons, and that's proven here with the electron configuration as well. Now the rest of the electrons, so all these other guys, these are called the core electrons. They are closer to the nucleus. They are held tighter because they are close to that positively charged center, and they are not involved in bonding. It's just trying to bring all of that full circle. All right, let me know if you have any questions.